Next, we're going to calculate the displacement of the boat. And therefore, when we calculate the displacement, we automatically calculate the associated draft. This is essentially the first part of the buoyancy calculations, because from these calculations, we will determine whether or not our boat will float, even before we get to the buoyancy section. The first thing we're going to do is calculate the volumetric displacement from our water plane areas. On my example boat, I have some water planes listed, and where they intersect the hull, we're going to get water plane areas. It's important to note that we are not going to calculate the water plane areas of the cantilevered steering assembly, and that's because this is not a watertight assembly, and therefore the amount of water it displaces is negligible compared to the amount of water that the hull displaces. Also, we're not going to worry about the bulkheads, even though they're shown in the picture, and that's of course because they're inside the hull, and the things inside the hull don't displace water. My water planes that I have shown in this diagram, there's one at the baseline, or base plane. There's another at my draft, which for my water plane areas, I'm assuming to be 6 inches. So this distance here is 6 inches. And then I have 1, 2, 3, 4, 5 more water planes, each spaced an inch apart. Now that we understand this, we'll start to fill out the water plane area table. The first step is to guess a draft. Since I'm required to have 6 inches of freeboard and my hull is 12 inches deep, I'm going to guess 6 inches of draft. This puts me immediately at my maximum. If I find that 6 inches of draft is not enough, I know immediately I have to redesign. If I find that 6 inches of draft is too much, I know that I'm operating in the safe zone and can reiterate to a more accurate draft. Next, I'm splitting my hull into 13 horizontal planes. I chose 13 to increase my calculation accuracy. Each of these planes are a ½ inch apart. The first plane is located at my baseline, and the 13th plane is located at my draft, not at the top of my hull. Remember, these areas are being used to find the volume of the boat that is sitting in the water, not the entire volume of the hull. Notice that on my diagram, I left out the ½ inch water planes, and that's just so that my diagram was not crowded. From CAD, I calculate the water plane areas, and then I list the Simpson's multipliers following the convention in the glossary. Next, I multiply each water plane area by its Simpson's multiplier. Finally, I sum the column and plug this total into my volumetric displacement equation. My volumetric displacement, which is going to be symbolized by this upside down triangle called del, is equal to the water plane spacing divided by 3 times the sum of the Simpson's multiplier times the water plane area. My spacing between my water planes was already mentioned as a ½ inch. And then my sum is 60,883.04 square inches. This gives me a volumetric displacement of 10,147.17 cubic inches. To get this to a more reasonable number, I divide this by the conversion factor. And now I can visualize this better as a volumetric displacement of 5.87 cubic feet. So now my boat is displacing this much volume of water. Since I'm operating in a specific density of water, I can multiply this by the density to find that my displacement, which is symbolized by a Greek letter called delta, is equal to 366.43 pounds. Now what I would do is I would take this number and compare it to the weight of my boat. If you remember on my weight spreadsheet, I found that my boat does in fact weigh 366.43 pounds. So I know that I'm displacing the entire weight of my boat, and therefore my draft of 6 inches is correct according to my water plane areas. And that's exactly why I modified my cinder block weight so that I can have this work out on my first iteration. If the displacement from the water planes and the weight of the boat differed by a significant amount, then I know my boat is not operating at the assumed 6-inch draft. I'd revisit this water plane area table and guess a new draft. I would stop guessing a draft until I felt comfortable that the displacement and the weight were close enough to proceed in my calculations. Now I'm going to calculate the volumetric displacement from stations. I have the example boat here, and now it's separated by vertical planes called stations. Each of these stations intersect the boat's hull is a station area. So my station area would be these areas. And of course, because my draft is only at a certain distance, I'm only calculating the station area between here. And for my station areas, I'm going to assume my draft is 6 1/16 of an inch. We are doing both water plane and station areas to increase accuracy. Besides, some hulls are better estimated by station areas than they are by water plane areas. Now we'll start filling out the station area table. This follows the same general method as the water plane areas. To start, I begin guessing a draft. I should be able to close in on a draft since I have an estimate from my water plane areas. Next, I split my boat into 11 vertical planes because I need an odd number of planes for Simpson's multipliers to work. Each of these planes are 7.9125 inches apart. I've placed my first plane at the forward perpendicular and my 11th plane at the aft perpendicular. From CAD, I calculate the portions of the station areas up to my draft. Notice that most of my station areas are equivalent since the mid-body and after portions of my hull are the same. Then I list my Simpson's multipliers following the convention listed in the glossary. And then I multiply each station area by its Simpson's multiplier. Finally, I sum the column and plug this total into my volumetric displacement equation. My volumetric displacement equation is the same as it was for the water planes. I have my h, which symbolizes my spacing between my stations. And then I have my sum of my Simpson's multiplier times my station areas. My spacing between my stations is 7.9125 inches divided by 3 times my sum of 3,847.10 square inches. And this gives me a volumetric displacement from my station areas of 10,147.73 cubic inches, which is very similar to what I found from my water plane areas. I'm going to divide this by my conversion factor. And the way it works out, I have the same volumetric displacement in cubic feet multiplied by my density of my water. And therefore, I find my displacement for my station areas is roughly the same. Just working through some of the significant figures, it comes out a little bit different. To 366.45 pounds. The first time that I did this, I assumed that my draft was 6 inches. I was trying to be the same as the water plane areas, and I found that my displacement differed a little bit too much, and therefore I increased my draft 1/16 of an inch, and therefore my displacement came out to be very similar to my weight of my boat. Now I would need to decide whether or not my boat is better estimated by my water plane areas or by my station areas. Of course, I can find from CAD which one would be better served, but I'm just going to choose my water plane areas because I want my draft to be 6 inches because that's my most legal amount I can have. If I have 6 1/16 of an inch, I know that my draft is illegal because I don't have enough freeboard. So I'm just going to use water plane areas for the rest of my calculations. Next, I need to find my design water plane area. So this is area of the water plane. Of course, I already have this dimension right here. Of course, this is my draft, so I have my design waterplane area. Finally, I calculate my pounds per inch immersion. This roughly tells me how much additional weight is needed to gain an additional inch of draft. So my equation for pounds per inch immersion is my area of my waterplane divided by the factor of 27.7 cubic inches per pound. I have an answer of 63.69 pounds per inch. This means my boat needs an additional 64 pounds before it can gain an additional inch of draft. And of course I don't need any more draft because I'm already operating at my maximum, but that's handy information to know.